All right, what's up, guys? Welcome to Chateau Smith, my back porch. Um, Sitting under our gazebo. We have a hardtop gazebo. Um, so, welcome. We said you're all part of the family, so here we go. All right. Um, so we had the first part of Unit 1, where we talked about um, the different pieces of the scientific method and why it's important to have all that information, and what you need to do to break it down. So you guys will be doing a do now quiz on that Thursday. And then this will be posted by the time you have class, or any of you have class on Thursday. You're going to do the do now first, then you're going to do this, and then we're going to go from there. So this we're going to talk about in this part of the unit. We're going to talk about data, why data is so important, what a theory is, scientific theory is, what a scientific law is, and we're also going to talk about metrics, and we're also going to talk about conversions and things of that nature. So everybody's favorite part of any of that. So, all right. So let's talk about data. So the types of data that we have available to review. There are two types of scientific data that we deal with. One, quantitative data. And whenever you hear quant, you should immediately think of numbers, okay? Discrete and continuous. Continuous can be continually broken down. That's when we're talking about decimals and fractions, and it continues to go down and down and down. You get longer and longer numbers on the right side of the decimal. Discrete numbers. Discrete numbers are numbers that, sorry, I'm trying to look something up right now. Quantitative data is the data that counts numbers. Each data set has a very unique numerical value. It's all about the numbers. Other examples include pricing, counters, measurement of objects, mathematics, projection of data, polling questions with scales from 1 to 10, closed-end types of questions, and they are more likely to be poll questions as well. So right now, what would be something that would be in the news we would be talking about in terms of quantitative data? Probably something to do with the presidential election. Okay. So when they talk about margin of error, and we'll talk about all of that, what's acceptable, what's not acceptable, and why these things are important, and why in the last couple of elections it hasn't even really followed what the pollsters are coming out with. So we'll talk about that a little bit more. But discrete, under the quantitative data, discrete are the integers and whole numbers. They cannot be measured. They can only be counted. Okay. Whereas continuous are the fractions and decimals that can be continuously broken down into smaller and smaller numbers. Okay. Then qualitative data, you hear the word qualitative, you should immediately think of a quality. And a quality is something that describes something. So qualitative data describes data qualities and characteristics. It's actually what you see. So we have nominal and we have ordinal. Okay, so qualitative data falls under nominal and ordinal. Nominal are the sets of values that possess natural ordering. They have, we talk about colors, we talk about sex, we talk about different things that you would be able to quantify or qualify, actually, not quantify, qualify by their specific colors. So colors being an example: green, red, Carolina blue, midnight green for the Eagles, navy blue, all that. You're able to quantify, or you're able to qualify that and make that a descriptor, because it's actually what you see. It's what you're able to see is what you're able to explain. And then when we talk about ordinal, we're talking about natural ordering. We're talking about sizes: small, medium, large, extra large, 2x, 3x, 27x, like me, and grades. We talk about grades because grades have a natural order to them. We have very specific, like 93 to 100 is an A, 85 to 92 is a B, things of that nature. So there's a natural order to the things that go to it. Just like sizes, there's a natural order. It starts small, gets bigger. Okay. So those are all of those things that you can use. Now, data from experiments is any numerical or quantitative data that you can gather and measure from observing your experiments. All of that's going to be, most of it is going to be quantitative. There is going to be some qualitative data that you get. Sometimes you put chemicals together and they change color, or something happens, or something changes. So those are the things that you will be able to see as you do your experiments. But more often than not, most of the stuff that you're going to do, especially right now, is going to be more quantitative, because you're going to be measuring, getting those measurements, and we talk about significant digits, things of that nature. And then the third type of data is the data from around us. Okay, what we see with the use of our use of current events, what we personally observe going on around us, and the subjectivity that we have to draw conclusions. Now, data from around us can be a little dicey because you can have biases, personal biases that come in. That could be a problem, but yeah, it's really what we see around us, and those personal observations, and it's subjective. So therefore, there can be some little bit of an issue when we talk about biases and whether or not, oh, well, did I see it because I want to see it, or did I see it because it really was there? So keep that in mind. And then the fourth type of data that we have available to us to review is computer science data. Okay, and that's this. Computer science terms are strings, which is a combination of keyboard characters, letters, numbers, symbols, and things of that nature that are put together. That's what a string is called. A character is just a single one letter, one thing. Could be one symbol, could be whatever. That's just a character is a single. Characters make up a string. Okay, and then the integers are the whole numbers. Very similar to what we know about math. Float are the decimals. Okay, and then when we talk about Boolean, there are 5 different types of computer science data. We're talking about questions that will be able to answer yes, yn, or tf. Okay, true and false, or yes or no. Okay, so computer science data, we have the character, which is a single mark, string, which is made up of characters, and it can be letters, numbers, and symbols. We have the integer, which is all the whole numbers. The Boolean, the float, which is the decimals, and then the Boolean, which is usually one with one character, either T or F or Y or N. So that's the data that's available and what we know in terms of that. And we'll talk more about data, why it's important, and how to get it, and how to get the things as we get more into this unit. So scientific laws. Scientific laws are the what in science. What we've been able to prove scientifically through numerous thousands, hundreds of thousands, millions, an infinite amount of experiments. Laws describe what will happen. Usually it's what you see. Okay, so scientific laws are going to be the things that you see that are going to happen. Perfect example. And we have multiple examples of laws. Perfect example so that we have there is Newton's law of universal gravity. Newton's sitting under the tree. All of a sudden, the apple falls, or the apple comes detached from the branch or the leaf, and it falls. Okay, so that's a law that over and over, and we can prove it now. Like I can drop my phone, and you can hear it drop, and that's gravity bringing it down to the center, bringing it to the center of the earth. Okay, other laws that we've talked about that we have are Newton's law of motion. Once something is put into motion, it will stay in motion until something acts upon it. We'll talk about that more when we get into kinematics in Unit 2. There's Boyle's law of gases, the law of thermodynamics. Laws deal with a narrower set of conditions. They deal with the what. Okay? It's what is going to occur, not why it's occurring. It's what will occur. An apple becomes loose from the branch, it's going to fall. That's the law. The law states that the apple, anything loose, is going to be pulled down to the center of the earth, or at least to the surface of the earth, because the gravitational pull is pulling from the center of the earth to pull it down. Okay, and then there's theories, scientific theories. Theories are the widely accepted and well-tested hypotheses. It's the why something happens. The theory explains what's going to happen, and it gives you that explanation. You have the cell theory, how cells have become available. The plate tectonic theory of Pangea and how everything was together and then they pulled apart, and all of those pieces and plate tectonics rubbing over each other that caused earthquakes and things of that nature. The Big Bang theory. I mean, it wasn't just a really good show. It was also a theory of how all the planets got here. And then the theory of evolution. Okay. How we all evolve over time, and we get into natural selection and things of that nature. So theories deal with the why something is happening. It's the explanation that has been constantly backed up over time, year after year after year after year. Okay. Just because something's a law and something's a theory doesn't mean it can't change, because it can. So just keep that in mind. If it's something, I mean, not if one time an experiment says, oh, well, I'm going to refute this law. No, you're going to refute it over time. It's got to be just as much time, probably, if not more, to disprove something than it is to prove something, especially something that's become regular knowledge in the scientific community. All right. So now to everybody's favorite, the metric system, and a brief history of it. So the metric system started in the 1790s, and it was during the French Revolution, and a new system of weights and measures, the Système International des Unités, or the SI, came into effect. Okay. Now, prior to this, and what it is replacing is people used to use their body parts, feet, noses, hands, etc. And usually it was based off of whoever the ruler of that area was. And every time a new ruler would come in, the measurements would change. So it got to the point finally in the late 1700s, as and much like with everything else, as technology started to evolve a little bit better and we had more ability to do things, the measurements were now able to be replicated over a same type of ruler, same type of measuring device, and things of that nature. The fact that that's why a ruler is why it's called a ruler is because it replaced body parts. And let's be honest, when the settlers came here, they were dealing with the same idea. Okay, they were dealing with the same stuff here. So they were measuring stuff based off of their feet, based off of their hands, based off of their noses, the size of their head. It didn't matter. That's what they were using to make measurements. And there was no standard way to say, okay, this is a foot. King Edward said this was a foot, but the King of France may have said, well, this is a foot. So that's why there needed to be a regular, systematic version to be able to do measurements. So the advantages. What are the advantages of the metric system? People in the United States would say nothing because it stinks. Nobody wants to do it. Advantages are it's universal. It's based on the tens. It's used almost exclusively universally throughout the world, except for here. And I will say to you that has cost us numerous times when projects were being done, scientific projects were being done. There was a space station that was being built. I believe France was helping us out with it. The measurements were sent. There weren't any labels with the measurements. They just looked at it and they assumed it was in metric, and it wasn't. It was in the US system. So they built all these specs and they wasted almost $4.2 billion building something that was useless because they did not use the metric system in terms of the measuring out. And then the French didn't convert it into metric. They just assumed it to be in the metric system because you would think that somebody, if they were sending you measurements, would send it into the system that you use. But hey, we're the US. We always bail France out anyway. So it is what it is. I'm sure we gave them money for it. All right. And why not the US? It's a great question. But really, it boils down to money. Congress would have to pass a bill or a law to change our current measuring system. And it has always been said by the opponents of changing to the metric system that it would be too expensive. You'd be changing all the speed limit signs. You'd be changing all the mileage signs. You'd be changing, I don't know, everything. You'd be changing all the signs. So apparently it would be too expensive to do that. So I don't think the U.S. is going to the metric system anytime soon. What is the metric? Well, it's based on the tens. And let's be honest, it's really not that bad. Okay. Usually you start with your base, and here that's where you are right here in this 10 to the 0. That would be your base spot. Okay. And then as you go each way, you're moving the decimal the opposite way. So here we go. So let's look at this. So here you have your base. If your base, say, was 7 meters. Okay, let's talk about measurements. If it's 7 meters and you want to find out how many decimeters it is, which way are you going to move? You're going to move this way, which means what? It's going to be how many decimeters make up a meter? Well, 10 decimeters make up a meter. So if you're moving to the right, you're going to move the decimal 1 to the right. Okay, so if you're starting at base, which is right here, and say it's 7 meters, okay, you go to deci, it's going to be 70 decimeters. Then centi would be 700 meters or centimeters. Okay, so it just works from there. And then you have, if you go into millimeters, which would be 1,000, it would be 7,000 millimeters. All right, but if you're going the other way, so if you're moving to the right, if you started at base and you're moving to your right, you're going to move the decimal to the right as well. If you're starting at the base here, and now you want to go into the larger scale measurements, so decameters. If it's 7 meters, it's going to be 0.7 decameters. You're moving to the left, so you move the decimal to the left. Then you go to hecto. You move the decimal one more space. Now you have to put a 0 in front of the 7 as a placeholder of the number, and it would be 0.07 hectometers. And then if it was kilometers, you move it over one more time to another space to the left. You have to add another 0, which now means it would be 0.007 kilometers. Okay, so keep that in mind. You move left. If you're moving left on the prefix scale, you're moving your decimal to the left. And if it goes past numbers, you have to put in zeros as placeholders. If you're moving to the right of it, you're going to move the decimal to the right. And again, if you have spaces and no numbers, you have to put zeros in as that placeholder as well. I'm going to do more with this. Don't sweat it right now. We're going to go over it. I'm going to go over a worksheet with you guys so that way you show it. So what are some of the SI measurements that we have? To measure length and distance, it's the meter. To measure the volume of an object, it's going to be the liter. To measure weight or mass, it's the gram. Whereas for us, weight is in pounds, but weight or mass is going to be measured in the gram in SI measurements. Temperature will always have Celsius as its measurement, and that's why freezing in Celsius is at 0. So they say that's at 0. Water freezes at 0 degrees Celsius, and then they build their chart from there. And then time is always based in seconds. So those are some of the SI measurements that we will be working with and that you need to know. Okay, so now we're going to talk about unit conversion rules. So this is the math part. Yep, here it comes. Ready or not, you're going to not be happy about it, but it is what it is. Unit factors are the key to changing the units of something. So an example that I'm going to give you guys is one of my favorite things in this world. and you knew it had to be food oriented because I'm fat. So it's Chester's chocolate ring donuts. Okay. So we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. 12 donuts equals 1 dozen. And unfortunately, at Chester's, actually, a baker's dozen would be 14. But we're not even going to get involved in that. We're just going to say a dozen donuts is 12. Okay. So you have 12 donuts, but 1 dozen. And what do you notice about the units that are matched with each number? They're different, right? So what's going to happen if you need to figure out how many donuts there are in multiple dozens? You need to set up a ratio. Okay. So let's say I'm particularly hungry one day and I want 5.5 dozen chocolate ring donuts. So here's your setup. Here's your ratio: 12 donuts over 1 dozen. That's what it is. Okay. So you have your 12 donuts equal a dozen. You set that up in a ratio: 12 donuts equals 1 dozen. All right. Now, what are you trying to do? You're trying to figure out how many donuts are there going to be in 5.5 dozen donuts. Okay. So you have your 5.5 dozen, not over nothing, equals 12 donuts over a dozen. So really, it's 5.5 dozen over 1, okay, equals 12 donuts over a dozen. So when you see something like this, what are you going to do? We're going to cross cancel. So you're going to be able to take out this dozen, and what's the unit you're going to be left with? You're going to be left with donuts. And that's what you need to get to. How many chocolate ring donuts are there in 5.5 dozen? And then what you do, you cross out your dozens, and you're left with 5.5 times 12, which figures out to be 66 chocolate ring donuts in 5.5 or 5.5 dozen donuts, or 5.5 dozen. It would be 66 donuts in 5.5 dozen. Again, we're going to do more examples of this. I will do more with this. I'll have a whiteboard that we'll be able to use that'll show you guys how to do this. But I just wanted to get this information, the data, the laws, the theories, and the conversion, and also the metric system, kind of down and dirty in one quick and easy video for you guys to have. And it's pretty simple. I'm not looking to reinvent the wheel here. We just need to make sure that you guys have that as a basis as we go forward. And the biggest thing is every mathematical equation I will give to you, but you have got to make sure that you include the units in your answer. If you just give me a number, I'm going to be like, is this 87.6 tomatoes, 87.6 hippopotamuses, 87.6, I don't know, chimneys, whatever. I'm looking at the top of my house. That's why I came up with that. So, but that's where we're at. Just so you know that, but that's where it is. You always have to make sure that you look at those things and make sure that you're including your units in every single one of your answers. All right. So I'll post this. This will get posted for you guys. You will have already taken the do now on the first lecture. Hopefully that will go well for you guys. And then if you have any questions, stop in, shoot me an email, shoot me something in Google Classroom. Otherwise, I probably won't post anything on Friday, or maybe I will. Maybe I'll post some stuff on Friday, but it'll just be a video part. It won't be an assignment or anything. And then next Monday, we'll start with assignment. We'll start with metric system, and we'll start with units and being able to convert units like inches to meters and things of that nature. So hope everything's good, and I will talk to you guys later. Deuces.